we did a question yesterday. How many of you guys were a little lost with the solution? How many of you guys are a little fuzzy? Okay. Like, how much of it was fuzzy? Most of it? Half?
I think so. Some of it.
Okay, so then I gave you a follow-up question. I gave you a follow-up question with a purpose because I said one of the critical...
Oh, no, I understood the question we did in class with the homework question.
Oh, yeah, the homework question. Okay. So, the reason what I did effectively was I took the question from yesterday and I tweaked it to give to you for homework. And I tweaked it in a particular way because one of the cases that you get is a classic example where it's very easy to overcount. And I'll be curious to see as we go through it, see how many of you, if any of you, or maybe all of you, recognize that fact and didn't overcount. And that recognition is really based on something I've already taught you. It has to do with, from a visual perspective, recognizing on your tree diagram that for a particular case you have an x by an x. So we have, and then of course you have the possibility, or not the possibility, you have a scenario where the tree actually can give you A, B, or B, A. It'll count both directions. Okay? And that's critical to this course. Okay? It's critical to this. So can you guys recap what the question was? What did I make of yesterday? It was how many? Okay, I created 4 positions, right?
Yeah.
And they were, what were they? Teacher, doctor, lawyer, student. Okay. And the overall thing was we wanted to, well, whatever. Let's just write this down. And then we're creating a committee, right? Or we're filling the 4 positions, right? We're filling the 4 positions from, what do we have?
One set of identical triplets.
One set of identical triplets. I might as well write it down here. So one set, no, I'll write this one. ID triplets, yeah.
2 sets of ID twins.
2 sets of ID twins, yeah. So
And
that
3
takes
people.
me to, we're at 3, and 4, that's 7 so far, right?
And 3 people who are visually distinguishable.
3 visually distinguishable people, right? And that adds up to a total of 10 people, right? Now, the name of the game here is, and then you can work the camera, right? Because I'm going to have to use up the whole thing. The name of the game here is how many visually distinguishable, that's key here, ways can this, I don't know what you want to call it, or we'll say, can the 4 positions be filled? So, again, as we discussed before, if you had, okay, so let's say these triplets. So let's say these triplets occupy the teacher, the doctor, and the lawyer. If they were to switch jobs, visually you wouldn't be able to tell, correct? So that's what this question is about. But this whole thing, this whole visually distinguishable thing is garbage when it comes to probability. And that's critical, okay? And people make that mistake all the time. Okay? People who have experience with this stuff make that mistake, okay? And you don't know what I'm talking about now because you don't really know what probability is. I haven't even given you a formal definition. Now we're going to be doing probability formally later, but maybe I'll at least touch today on why you can't use this for probability and why it's such a big no-no. Let's at least go through the answer to the question. Okay, so in this scenario we have 10 people, right? But we only have how many visually distinguishable objects?
5.
1,
5.
3, 6 is it?
6.
6, right? Because we have one, so let's just draw them. We have one set of identical triplets. So here are our identical triplets. We'll make them stars, right? These are our triplets, one set, right? We have 2 sets of identical twins. So maybe we have a pair of circles and sure, a pair of squares. And what else do we have?
3 visually distinguishable.
Okay, so I don't know.
Diamond.
What do you want to go with? Diamond, triangle, and which one?
Hexagon.
I'm not doing a hexagon. I'm gonna do a
Parallelogram.
smiley face.
Oh, sorry.
Okay, so that's six. That's six unique or six visually distinguishable object types. And the total sum of the objects is still 10. So as we discussed yesterday, we're going to go with cases for our solution, right? Okay, so anybody want to get the ball rolling? Chris?
This one could be all different.
All different. Now, you have to keep in mind that we have 4 positions, okay? So, if they're all different, that means you need one of each, or to say it a different way, every single object has to look different. And if every object has to look different, then you're only taking one of it from whatever pool of these 6 you're taking it from. And since you're only taking one, there has to be at least one of each in every pool, right? So how many of these 6 options are viable options?
6.
All 6, right? So, do we care about order?
Yes.
Why?
It's different.
Put up your hands.
Depending on who you take first, it's different what positions they take. So, teachers, doctor, lawyer, student.
Yeah, even if I go star, circle, triangle, smiley face, there are different ways I can do that. Because as I organize them from left to right, if you will, you can think of them being slotted into these different positions. I could rearrange those same 4 shapes, and that would be a different outcome. And it would still be a visually distinguishable outcome because we presume that, I don't know, picture like 4 desks with little titles like teacher, president, blah, blah, blah. So you can see, oh, if I take Ronald and I put him at the teacher position, if I go again with Ronald, I move him over to the VP, that's a different visually distinguishable outcome, okay? So we have a total of 6 visually distinguishable pools from which we can take a single. And how many singles do we need to take? 4. And the order counts, so I can write a
6 choose.
Okay. Now choose. If you write choose, that means you don't care about the order.
Oh.
So you could do that, but then you're going to have to multiply by 4 factorial to inject the order back in. So 64. You can use your calculator, or you can recognize, hey, this is the same thing as 6 factorial. You're taking 4. 6 plus 4 is 2 factorial. Those are the 2 you're not taking, correct? And that gives you 6 by 5 by 4 by 3.
360.
Is that 360?
Yeah.
Okay. And that look okay so far? So that's good because Crush started with a straightforward case, which is a good thing. Okay. We're not getting this, right?
We got it.
That is actually filming this?
Yes.
That's badass. It's like a wide angle thing?
Sir, if you say it right now, you know it goes in there.
Yeah, whatever.
Edit it out.
Case 2. Okay. What do you got?
Just
Michelle?
say one different.
2 same, 1 different. You guys, I see you, but you're late. Let them in 2 minutes. 2 same, 1 different. When you say 2 the same, 1 different, that to me adds up to 3 people.
So that means 2 same, 2 different.
You want 2 same, 2 different. 2 same, 2 different. So, again, now we're in a situation whereby what we're going to do, and guys, stop me if anything doesn't make sense. So, Aaron, stop. Is everything good so far?
Yeah.
On this one? So now we're in a situation where you're going to take advantage of a technique whereby we're going to make our choice now without order, and then we'll inject order at the end. Okay? We're just going to first figure everything out in terms of basically a combination, and then inject order at the end. And the reason we have to do that is because we have a situation where we're going to have multiple objects that are the same. In this case, all the objects were different, so it was very easy to just say, oh, I'm taking order. This situation is different. So let's talk about 2 the same. How many of these 3 groups can provide 2? 3. And since I'm not taking order now, that's going to be 3. And when she says 2 the same, she means 2 identical objects. So we're not going to write choose 2, as Milan was pointing out yesterday. We're going to write choose 1. Because 3 choose 1, The 1 doesn't mean that you're only taking one person. The 1 means that you're choosing one of these 3 groups to be a double choice. Make sense? Okay, so we can even write that. We can call this variable x. You can say choosing one of 3 groups that that can do so to provide 2 identical people. Because not all of the groupings here can provide 2 identical people, right? 4, 5, and 6 can only do singles, right? So what are we at now?
2 different.
2 different?
Yep.
Okay. So if it's 2 different, we're after singles now, right? So imagine that we knocked out, I don't know, triple star to use as our double. So imagine we've got double star. Now we need 2 different looking objects, right? Is there, can I get that from any of these?
Yeah.
Yeah, because I just need singles, right? So how many objects do I have left?
5.
Or group, 5 groups, yeah.
And you only choose one.
And I'm only choosing, well,
2.
am I choosing 1 or 2?
5 choose 2.
But if you already chose 2, like.
But how many? Okay, but what? Look, she wants 2 same, 2 different. So 3 choose 1, then I just went star star. I got a couple stars in there. How many more people do I need to make 4, right? And they've got to be different. So I have 5 different groups left, and from them I got to choose twice. In other words, I got to take circle and triangle.
But if you chose circle though, then you don't have that group.
Say that again.
Like if you chose circle, then.
Okay, if I don't choose circle, then I still have 5 options because now I can take a star. 1, 2, 3, 4, 5. Making that first choice, 3 choose 1, eliminates this, this, or this. If 3 choose 1 eliminates triple star, well, it eliminates this as a choice for my next choice. It eliminates this or this as a choice. Because even if let's say I took double star, can I leave, there's still a single star in there. Can I leave that as an option for the next one? No, because that will create triples. So once I use one of these double choices, it's not allowable again to be chosen from for the 2 singles that look different. So once this is out, I have 5 options left. Even if you took double square, then these are options, but it's still 5 options. And you need to take 2 of them, a single from each option. So it's 5 choose 2. I'm kind of leading you to, I'm trying to lead you to the dangerous case by writing my variables up top. Why is this a y? I'm giving you the answer. Why is this a y and not an x? Why is this a y and not an x? You're choosing people. You're choosing people here. You're choosing people here. Michelle.
It's different positions. That's how you.
No, no, Crush.
Because the first case is 2 identical, so it represents one of those is x, and then the other one's all distinguishable. Therefore, each one represents a y.
Yeah, I'll just reiterate what he said. This represents choosing doubles, and this represents choosing singles. So in your tree diagram here, if you went with star for this one, I'll do a little zoom in here. If in part of the tree here, this would go like this, let's say star, star, agreed? Or let's say you could have gone circle, circle, or you could have gone square, square, right? After star, star, could you go circle, square? Sure you could, right? And after circle, circle, could you go star, square? Is that allowable? Sure you could. And after square, square, could you go, I don't know, circle, star? Are any of these branches counting the same scenario in a different order? No, they're not. Because this is these are double choices. Actually, this should look like this. Should be like that. See, you have double star here, and then those are singles. Okay? You'll never see this in reverse. You don't see anywhere here. You cannot have double star with the first branch of this, right? Do you see this in reverse in this tree? You can't, because the first branch of where are you guys going? Oh yeah, you said 2. Okay. Because the first branch of our tree is a double choice. Okay. How many of you guys see it? How many of you guys are still lost? Okay.
Sir?
Poker is a classic one. Because in poker, where you make the mistake is with two pairs. Whatever, it's coming up. I'm giving you the answer. It's coming up. You'll see. Anyhow, I'll get to your question in a second. So, 3 choose 1, 5 choose 2. So have we chosen the 4 people? Yeah, we have, but now we have to inject order. How many positions are there? 4 positions. 4 factorial. But how many of them are identical? 2. So we divide by 2 factorial, right? So that's 3, that's 5 times, I'm not going to do it right now. Help me. I should be doing this. We can do it in our head. 3 choose 1 is 3, right? That's going to be 5 factorial over 2 factorial, as well as divided by the difference, which is going to be 3 factorial, right? And then this is going to be 4 by 3, which is 12, right? You can do it with your calculator, but it's also good for you to get the practice. So what do we have? We have 5 by 4, and then divide by 2 becomes 5 by 2, which is 10. That's 120. Is it 360 again? Or am I way off? You guys tell me the number. Is it? Is anybody else signing off on that?
Sure. How'd you get 4 factorial and 3 factorial?
This just represented who was in play. Let's say a couple stars, a square, and a triangle. But it didn't create order. I need to create order because I have 4 positions. So I have 4 objects, I multiply by 4 factorial, but 2 of the objects are the same. Divide by 2 factorial.
Okay.
Got it?
Yes.
How many of you guys don't understand how I did this math? You're all good? Okay. So 3 choose 1. How many? Or
Where did
different?
the 3 come from?
At 3?
Yeah.
You choose 1. You understand where this came from? N factorial over n minus r factorial over r factorial. And then this is 4 times 3 times 2 factorial. The 2 factorial is where we left.
I understand that. I understand the 5 factorial.
Okay, we're good. Yes.
Sir, for this case, can't you have technically like a square, circle, star, star? Would that work still?
Square,
Circle,
circle.
star, star.
But do you have that in this multiplication?
Yeah.
Yeah, I know that. But before,
No.
that was my point.
Okay.
My point is that in this portion of the multiplication, you have yet to inject order. You'll see what's coming. I don't know if you pick it. You'll see what depends on what case you pick next, but you'll see what's coming. Who already knows what I'm getting at? Who knows where I'm going? Okay, we'll see. Okay, so we've done 2 cases, right? We've got case 1, we've got case 2. What's next?
These 2.
What are you coming up with for case
So it
2?
means that it would be,
Just pick one. Yeah, pick the
it
next
would
one.
be all different.
Okay, all
We
different.
already did that.
Can we do all different?
So it would be 3 same.
Why can't we do all different?
Because you already did it.
Oh, sorry, I thought you were going to say all the same. Can we do all the same?
All the same means all different.
Why can't we do all the same?
There's not 4.
There's nobody that can provide 4.
So, 3 same.
Is there anybody that can give you 4 identicals?
No, but I mean like 3 same. Can we do 3 same?
Yeah, let's do 3 same. I like it. You're leaving out the ones again. I like it. Okay, so 3 same. 1, we'll call it 1 diff, I guess. It's 3 same. Writing 1 different, I guess, is kind of redundant or whatever. Okay, so 3 same. There's only one that can provide 3 the same, right?
Yeah.
So you can write it as 1 choose 1, or you can just write it as a 1. Then you want the rest to be different. We need 3 more people. Any of the remaining 5 options can do that, right? Stop me if I make a mistake. So it's going to be, well, we only need 1 more of them, because this represents a choice of 3 people. Right? So it's going to be 5, C1. We're going to inject order with 4 factorial, but 3 of them are the same. So that's a 4, because 4 factorial is 4 by 3 factorial. 4 by 5 is 20, by 1 is 20. Right? What else do we have?
The last
3, 2 identical.
2. Say that again, Kierman?
I know 2 same and 3 different.
No, 1 same.
Yeah, 2 same. No, it's only 1.
2 pairs of identical.
2 pairs of identical. Is that the last case?
Yeah.
2 same, 2 same. Are you getting this? Because this is the most important part.
Right in the corner.
Oh, whatever.
Or which side?
Oh, okay.
2 same. What is this? Case what?
Case
5.
5.
2 same, 2 same, 1 diff, right? Okay. So,
Wait, sir?
yeah.
How's that possible? 2 same.
Oh, sorry. 2 same, 2 same. Two pairs, right? 2 pairs. Damn it. We're not going to have a problem.
1, 2, 3.
It's going to be easy. Because we're going to do it. We're not going to, it's easy. It's not going to present the problem I wanted it to present. I don't think. Okay, how do we do it? Go. How do we do it? How many can provide doubles?
3. 3, choose 1.
3 choose 1?
Oh, 2, 2, 2.
Okay, actually, no. 'Cause
No,
we can, yeah, no. Okay,
That's
let's,
twice.
you want to go down the 3 choose 1 road? Okay, let's go down the 3 choose 1
Wait.
road. Okay, let's go down the 3 choose 1. Good. I like this. Okay, we're going to go down the 3 choose 1 road. Can we get it this way?
Yeah.
Yeah.
You can.
have to inject the order in the end, right?
So 3 choose 1 means choosing one of these 3 to give you a doubles, right? And then you're going to say, oh, there's only
Choose 1.
You're going to say there's 2 choose 1, and then what are you going to do now? What are you going to do? Order? You're going to put in order, right?
Yeah.
Okay.
Be loud and be quiet.
But wouldn't it be 3? It would be 3 factorial.
Well, no, there are 4 objects again.
Yeah, so it would be 4
4 factorial divided by 2 factorial over 2 factorial. If you know what's happening now, don't say anything. Okay. So, agree? That's...
Oh,
What?
okay.
Oh, don't own me.
No, because it's the thing that we did yesterday, right?
No. So 3 by 2 is 6, right? So what is that? That's 4
36.
by 3. Hang on, that's 12, right? 12 divided by 4 is 3. 3 times 3 is 9. Isn't it just 18?
No, that was 6 by 6, and then be 36.
This is 3.
Multiplied by 2.
3 by 2 is 6.
6.
And then
That's
4 by
6.
3 is... oh yeah, it's 6 by... It's 36?
Yeah.
So 36 you say, right? Okay. Now let's try it a different way. Let's just try it a different way and see what happens. Or how about this way? How about we just say, because we're choosing we're choosing a pair of identical twins twice. So how about doing it this way? How about saying, how many of them can provide a pair?
3.
All right. And let's take 2 of them, right? Meaning, I'm taking double star, double circle, or I'm taking double circle, double triangle, or I'm taking double star, double square, right?
Aren't you left with 1?
What?
Aren't you left with 1?
Yeah, there's always going to be one out. Like,
Yeah, because it's like if you choose 2 of these doubles, so for example, if I choose 3 and 2, then I'm only left with 1 that can provide me that.
I need 2 pairs.
Are you talking about 2 pairs?
I'm
Yeah,
taking
2
2.
pairs.
So 3 are the objects that can give me pairs.
Yeah, and you're taking 2 from them.
I'm I'm choosing 2 of the 3 objects, not singles.
Yeah.
So meaning, I'm going with double star, comma, double circle, or I'm going to go with double square,
Doesn't matter if
comma,
it's over.
Yeah.
double star, right? Yeah, and the answer is there are going to be 3 ways that can happen, right? Okay. And then I'll do your order thing.
Your order.
Right? 4 factorial over 2 factorial, 2 factorial. What's the answer? The answer is going to be what? 18?
Oh, why is it that?
The answer, if my thinking is right, without doing any math, the answer should
But
be
18 times 2 is 36.
Is the answer 18? The answer is 18? So what's up? Which one is right? Top or
Whoa, that's so trippy.
bottom? Which one is right? How many of you say top?
What the hell? Why is it doing
How many of you say bottom?
Is it bottom?
None of you are voting.
I don't know the answer. It's the bottom,
Wow,
right?
it's the
Okay.
bottom, because if you told me at the beginning that they don't owe me, then it means that it's the bottom.
Bottom's right. So the top is
why,
over.
why does that happen?
Okay, go back here. Let's put an X on this. Let's go with your method here. What does X represent?
The
choosing of
Oh,
doubles.
the doubles. And then the
And what
second
does
would be
this represent? The
Doubles
choosing
again.
of
doubles again.
doubles. So you know what this?
Oh, you did.
This will create a tree diagram that could go like this, for example. Star, star, circle, circle. But it can also have a branch that will go circle, circle,
Stars.
star, star. So you're counting order here. You're counting order in which you take those two people. But then guess what you're doing? You're also putting order back in again for all four.
If you just left it alone, it would have been fine, right?
Left what alone? No, it wouldn't. It would still be wrong. Because this is an injection of order for 4 objects with 2 identical people. And this is just an injection of order for the order in which you chose the 2 identical groups. It's so way off. So if you wanted to fix it, you could take this part right here and divide it by 2 factorial, right? If you wanted to. And then this answer becomes 18, right? Or
Just did the easier.
better to just go that way. And that's what people make a mistake with. How many of you guys follow this? Rachel, no idea what the hell I'm talking about?
Kind of.
Okay, what's kind of not?
I don't really get when you multiply 4 over the 2 factorial. Like, where does that come from?
Oh, this?
Yeah.
How many different ways can you organize these letters? A, L, L, G, G. How many letters do you have? So if you care about, and then you have double L's and double G's. Got that? Do you guys understand that? That's why, like, for example, when we do probability for 2 pairs in poker, right? Sometimes people will say, okay, I'm going to take the first pair, and then I'm going to take the second pair. But what you don't realize is you're creating a tree that says Jack, Jack, Queen, Queen is different than Queen, Queen, Jack, Jack. It's not. The order doesn't matter.
So why did you put 4 again? Okay, I get the other purple. Why?
Because there's 4 positions.
Oh, there's
Oh,
4
this is the
positions
same
there.
logic as all the
Yeah.
other. Again, look, all of them have a 4 factorial. All of them have, well, this one doesn't need because
That
we
one
just
is-
injected.
Yeah, got
Here
it.
you can inject order right away. So. If you wanted to do this way, you could have gone, or you could have gone for this one 6, C2, right? And then you could have multiplied by 4 factorial, but there's no need to divide by anything because they're all different.
Yeah.
If you want to do that.
But
So,
how come,
yeah.
why do we say though 2 same, 2 same? Like, I get the
You
logic.
can write 2 pairs if you
2
want.
pairs, yeah.
Yeah, fine, 2 pairs. 2 pairs. Good?
So you have to change everything else to pair.
What?
Nothing. 2.
What?
Oh, no, a pair is.
Whatever. That's the same. You guys know what I mean,
Yeah,
right?
yeah.
A pair of one type, one looking person, one person that looks one way, and then another pair of 2 hamburgers and two orders of hamburgers and 2 orders of french fries. Okay, so are those all the cases? We didn't miss any? Okay. So add them all up. What is the first case? 360?
One
Yeah,
of them is
please.
Case 3?
20.
20,
No,
0,
0 was case
20.
20,
20.
18.
18.
And what does that give us? 720, 740, 758?
Yeah.
Yeah.
I didn't even get it.
I want you guys to double underline your answers on quizzes and tests, please. It makes it easier for me to, I'll mark more favorably if you do. It makes it much easier for me to mark. So your final answer is a double underline. Because that way I just go straight to the double underline to see if it's correct, and then I give you full marks, and if it's not, then I can go dig and look for part ones. So double underline your final answer, not box, not. Okay, did you guys learn something there? Okay. So, do you want to, like, if you guys in the back know what's going on, you don't have to follow along with us here. You can go ahead and do whatever you want. Totally fine.
Whatever we want.
Huh? Yeah, as long as it's quiet. Whatever you want. Whatever you want. Okay, so I'll just make a quick note about probability, because we're going to be studying it later on in the course. But I'll tell you why people get into trouble for probability in situations like this. Let's say I asked you, yeah, might as well just do this. This is very important. Let's focus in on, what was the last case that we just did? Okay, a bit about probability. This is going to be an aside. Let's abstract case 2. What was the last case? What was the last case? 5? It was two same, or 2 pairs. And we did, what did we do? Oh yeah, we did 3 choose 2, and then we just went like that. And that came to 18, right?
Yeah.
Now let's ask you, if somebody asks you, what's the probability of getting 2 same for the 4 positions? Now you should know, let me tell you, probability is a percentage, and it's from 0 to 1. And the reason why it's a percentage is it's the ratio between successes, the number of ways you can achieve success, to the total number of ways the situation can come out. So I might as well give you that definition. So the probability of success, let's say A is success, is going to be equal to the number of ways the success can turn out divided by, you've seen S before, universal set, divided by the total number of ways the scenario can turn out. But there's a critical aspect here. It's the number of equally likely, physically possible ways. Equally likely, physically, it's not a visual thing. Exactly, it's a physical thing. Probability is a physical thing. If I have, let's say, I don't know, in these lottery things, let's say I have a chute with like 106s in it, like whatever, they have like the little random balls with the numbers, right, that come out. So picture like 100 of them, I don't know, picture 100 of them like, I don't play the lottery, but I remember seeing this thing as a kid where like they're all scrambling, right? So imagine there's 106s, let's say, and 3 come out. Now let's say, instead of them moving, actually I'll just imagine them in a row. Let's say 100 of them in a row. Let's say the first 3 6s drop out, as opposed to the last 3 6s dropping out. Okay? In both scenarios, your visual result is the same.
It doesn't matter,
right?
order.
Visually, those are the same thing. But in terms of probability, in terms of the number of ways that the scenario, that physical result can come about, are they the same? They're different physical results. Why? Imagine that I had 100 6s and I had 50 3s. Okay, so you picture 100 6s, right? Right? Let's put another one there. But only, let's say, 53s. Now, what's more likely? To get 3 6s or 3 3s? 3 6s, right? In fact, it would be double the likelihood, right? Which would make sense because you have double the number of 6s. Well, if you're going to say that taking the first 3 6s is the same scenario as taking the last 3 6s, then you're not going to get double the probability for that scenario. Why is the probability double? Because you can take, these 3 6s can drop, or those 3 6s can drop. There are more physical ways that you can get 3 6s to drop out. You guys see what I'm saying? That's why the likelihood is greater. But the problem is when they teach all of these visually distinguishable questions before probability, people just automatically think, oh, when we do probability, well, that's my numerator. They're like, well, the total number of ways I can get 2 pairs, or 2 the same. And they're going to say, oh, well, it's 18 ways you can get 2 the same. And then they're going to divide by the total number of ways this thing can come out. And their NA would be wrong. So my question to you is this. How do you calculate how many equally likely, physically possible ways there are that you can get, and I'm thinking about it in my head right now, 2 of the same and 2 of the same.
So 2, 6 is 2.
And I don't even have the answer.
5 objects there.
You're saying you have 5 objects?
Yes, because out of triplets, you
Yeah.
can choose it in 3 ways.
That's good. So you're saying for the triplets, you can you have 3 choose 2. Because there are 3 ways you can take. It's actually tricky because you have to break it up into cases, right? If you use these guys, it's easy, right? Because there's only one way this can provide doubles. And there's only one way that this can provide doubles. But if you're going to take 2 stars, do you see that there are 3 physical ways you can take 2 stars?
The first 2.
You can take these 2, you can take these 2, you can take these 2, or 3 choose 2.
So then you have to take that as separate.
So the number is different. Okay, we don't have to go, I don't want to go any further because then I'm going to get off track. And we're going to come back to this and revisit again from scratch, okay? Okay, so probability is different than number of visually distinguishable ways. And the way I'm going to do it with you most likely is, and I did this last year, I'm going to give you guys all, split you guys up into groups of like, I don't know, 3 people a group. Let's say we'll get 10 groups. And each group will get like, I don't know, 10 blue jelly beans and 5 green and 3 red or something, right? And I'll say, okay, go. And each group is going to take out, let's say, 3 jelly beans. And I'm going to make, and then when you're done, you throw them back in and mix them up again. And I'll have a laptop running. And I'm going to record how many I'm going to record, what am I going to record? Oh, I'm going to record the number of, let's say, blue jelly beans that you got. Okay? Now, mathematically, there's going to be a theoretical probability that you can calculate. And what will happen, or what should happen is, you know, I might get some data points like this, but eventually it should flatline around the theoretical probability, as long as you don't do what Chris Lee did last year and eat one of the jelly beans and then piss me off and make me have to think for an hour after why the numbers are different and oh my god, my head hurts so much. It's just because he literally ate a jelly bean. And if I catch anybody eating a jelly bean, you're dead. I'll turn you into a jelly bean. There was a big debate in the math office over this. Like Mr. Gallo was saying, no, it could still be. It's good. And I'm like, there's no way because we're already this far. Because the more data you have, it's harder to move the data, right? It's like if you have two trials in that are like that take you to here, well, the next trial can have a big effect. And if you've already done 100 trials and you want to be here and you're like trending down here, and it was perfect. And actually, when I back calculated, I was like, how many jelly beans did you? It actually was it was bang on. Like I can't remember how many jelly beans he ate, but it made sense because the theoretical probability was lower, right? And it was because it was the jelly bean that he ate, which we were tracking, right? But the point of it is that if you have 10 jelly beans, right, that are blue, and let's say 5 that are green and then 2 that are red, what do you expect to see more of? Blue. Okay. You know, getting a blue, a red, and a green, even though they look the same, the likelihood of getting more blues is greater because there are more of them. So it's not about visually distinguishable probability. Okay, so we have 2 options. I'm tired. I'm talking. We can, I can take up more questions that you had from previous days, or I can start teaching some new stuff.
I have just one question.
You have one question? Who else has questions? More? Is it Ken? So Ken, Michelle, who else? Rohan. Arthur,
we have the same question we studied yesterday, and we just want to ask.
Okay, so can you erase some of this stuff? Yeah?
Should we stop it?
Oh, I have 2, sorry. Is that okay?
I think we're... Oh, and then I gotta take you guys into set theory in more detail. Multiple rings and all that. We still have to do all that. But whatever, we're fine.
Are we like on track?
Oh yeah, like in terms of... Oh yeah, we're on track. We're probably... typically I usually move fast, so we're probably still ahead. But what I like to do is I like to move quickly, and then that leaves more time for me to take up more questions with you guys, and then it all evens. It all evens. Okay, so what do we got, Michelle?
I have 2. Page 245, question number 6.
We'll start with that.
Okay.
So, 245, number 6.
Okay, so how many 7-digit?
Louder.
How many 7-digit even numbers?
7-digit even numbers. Just curious, are we allowing for lead zeros? No.
No.
Right? So
Less?
we're saying that.
No, it doesn't have zeros. Just at the end of the question.
Oh,
it
okay,
gives you
okay.
digits.
How many 7-digit even numbers? Yeah.
Less than three with
Million.
6 zeros, yeah, 3 billion.
3 billion?
Million, yeah.
Yeah.
Can be formed using all the digits 1, 2, 2, 3,
Hang on. All digits.
1,
Yeah.
2, 2,
Yeah.
3,
Yeah.
5, 5, and 6.
Okay, so I'm assuming that there are.
7.
So you can't start with 3, 5, 5, or 6. So I'm gonna start with 1, 2, or 2.
So the only way I can make an even number is ending it in 2 or 6.
Yeah. that's
Agreed?
Yeah.
Less
You
than
can't
3
start
times
with
the
5.
two ways.
Oh, you can't start with 3, 5.
But yeah, that's true. I cannot start with 5 or 6.
No, you can't start with 3 either.
And I cannot start with 3 either, you're right.
You can
So you can
only
only start with 1, 2, or 2.
We can only start with 1
You have to end
or
with
2.
2 or 6.
Yeah, 2 or 6.
So let's see. Let's talk about a case here. Should I write down what you guys just said? Who wants that information written
Yeah,
down?
might as well.
Okay, so you must end, so we'll say solution. You must end in, you guys said
2 or 6.
2 or 6.
Cannot start. Can't start.
Start with 1 and 2.
Can? Well, let's just talk about what you can. Or you must,
You can't start with 3, 5, 5, or 6.
let's just write that down. You can't start with 3, 5, or 6. Therefore, you must
Start with 1,
1 or 2. Right? Okay, so let's do some cases here. You guys have anything? So, let's see. If I start with a 2, here's the thing. It'll all work itself out. Why don't we start with a 1? You guys know, and by the way, when I put quotes around a number, I like to do this sometimes because very often I'll write down like multiplication. You've seen me do stuff like this, like 4 by 3, by 5, and so on and so forth. These don't represent numbers, these represent options, right, in the tree. But when I use a quote, I mean that I'm locking in that space at that number. You see what I mean? So when I use quote 1, I don't mean one option, I mean I'm going to literally drop the number 1 into that spot. So we have 7 spots, right? 1, 2, 3, 4, 5, 6, 7. So we are literally dropping that in. And I'll put an X here. What do you think I mean by the X?
But it's like it has one, like
It's locked.
Yeah.
Position is locked. Yeah.
So we can do it without cases, only press 1 time.
Okay. Yeah. Can I finish? I'm just gonna go down my path, and then we'll do both. I like less cases too. So, how many of you guys want me? How many of you guys want me to finish this path? Okay, so I'll finish, and then we're gonna do that. Okay, so if we start with a 1. Well, here's the thing. We start with a 1. How many options do we have to end with? Still, 2 options. I could still end with 2 or 6, right?
Right.
So start with 1, end with 2. Okay? So I'll do that. And those are out. You guys follow? So I started with 1, I ended with 2. That's allowed, right? So guess what happens to these? These are gone now, right? And how many positions are there left to choose? 5. Right? Two of the positions are gone, right? And how many? What are the numbers left? I have these 5 numbers. So does the order matter? Sure it does. There are 5 left. 5 factorial. But how many of them are identical?
2. No.
Or a pair of 5s. Pair of 5s. Okay, so that's that case. You guys see that?
Yeah.
Again, I locked a 1 and a 2. I've used up 2 of the 7 positions. There are 5 positions left. We've got to use all the numbers. You've used up 2 numbers, 5 positions left, 5 numbers left. But the thing is, what are the numbers? Well, if I've used up the 1 and the 2, you can see that the numbers are 2, 3, 5, 5, 6, so the double 5 has to be taken into account there, right? So then I could say case 2, start with 1, and then end with 6, is it?
Yeah.
So now you're taking this out and you're taking this out, right? But notice it's a little different. Now you have 2 sets of doubles. So your answer is going to be 5 factorial over 2 factorial and 2 factorial, right? And now we're going to go, what's our other option? Start with 1 or 2. So case 3.
Start with 2.
Yeah, start with 2. If you start with 2, can you still end with 2?
Yeah.
You can. So if you start with 2 and you end with 2, guess what? You have no more 2's left, right?
One double.
But you still have a double. So you have your 5 factorial over 2 factorial, right? And then what's the last case?
It would be start with 2 and with 6.
Start with 2 and with 6, right? Now if you start with 2 and you end with 6, how many doubles do you have? 1. So you also have 5 factorial over 2 factorial. Do you guys agree with that so far?
Yeah.
Okay, so I think we have a lot of similarity here, right? Are there any other cases? So if you take a look at this, case 1 was 5 over a double, but then the other 3 were the same, right? So it looks to me like you have the solution is, and you guys will double check it, tell me if I'm wrong. 3 times 5 factorial over 2 factorial plus a single 5 factorial over a double. Is that right? Just scan the board, please. 5 over 2, 5 over 2 and 2, 5 over 2, 5 over 2. I think that's right. What does this come out to?
210.
Check the back as well.
The back is 210.
Yeah.
Okay. Any questions on that method? Naomi, does that make any sense? Yeah? Yes?
Could you please do question 3?
Wait, no. Milad's going to do it different. He's going to do it faster, I think. I want to see that. Hang on. Aaron?
Where did the 3 come from?
Oh, because this is the same thing. You add up all the cases, right? So, look. 5 factorial over 2 factorial plus 5 factorial over 2 factorial plus 5 factorial over 2 factorial plus 5. Okay. Just 3 of them. Okay, Milad, you want to do yours?
It doesn't work.
So, what do you mean it doesn't work?
There is nothing like that.
Because when you put 2, there are like 2 ways for the beginning to be 1 or 2. You don't know if there's a pair or if there's not, so you can't do it.
So you need to break it. Okay, so you're going to go with this method. Okay, anybody else have a different method? Okay, so we're signing off on that. Okay, what was the next one?
It was page 280, 21B. Me and Milad tried to do it, but we couldn't get it.
21B.
So should I read first the...
Yeah, go ahead.
Okay, so there are 18 students involved in the...
How many?
There are 18.
Loud, nice and loud.
Okay, so there are 18 students involved in the class production of arsenic and oil plates.
Yeah.
Should I read A in order to read B? Maybe they're...
Yes,
Okay.
read the whole thing.
In how many ways can the teacher cast the play if there are 5 male roles and 7 female roles, and the class has 9 male and 9 female students?
Okay, so I have 9 male, 9 female, but then in terms of roles,
5 male.
there are how many? 5 male?
5 male and 7 female.
So
But
5
this is
male
A.
roles and 7 female roles, yeah. And
Now-
so A was how many ways can you cast the play?
Mhm.
Okay.
So now B says, in how many ways can the teacher cast the play if Jean will play the young female part?
Is Jean with a J or G?
J-E-N.
J-E-A-M.
Jen.
Jean.
Jean. Okay, Jean.
John
I don't know.
will
Jean.
play the young female part only if Jovan plays the male lead.
Wow. Young
Jovan.
female
Only
Role,
if.
yeah.
Yes, only if Jovan plays the male lead.
And then, so that's locked, right?
Yes.
And then what else is locked? Jovan is Jovan.
But Jean can play only if Jovan. So like if Jovan doesn't play them.
Yeah.
See, that's what we were thinking.
Okay, no, wait.
Should I read again?
Yeah, read part me again.
In how many ways can the teacher cast the play if Jean will play the young female part only if Jovan plays the male lead?
So basically what you're saying is, if he plays the male lead,
She's dependent.
That she's dependent, yeah.
He's independent. It doesn't matter.
but if he doesn't play the male lead, then all other options are on the table?
Yeah,
But if
essentially.
We have to break it.
If he plays the male lead, it doesn't necessarily mean that she's going to be.
Yeah, exactly.
Well, it doesn't say that she will play that?
No, it says she'll only agree to, but it doesn't
Yeah,
necessarily mean she's chosen.
if.
Let me read
John
it, but with,
plays.
well, now actually let's look on paper. 17B?
Yeah.
21.
No, 21.
21B. In how many ways can the teacher cast the play if Jean will play the young female part only if Jovan plays the male lead? She will play it. Okay.
Oh, she will play it. She has to.
If she will.
This is very badly written.
I know.
Will play the young female part. So if he doesn't play,
Sir,
That
sir,
word-
let me finish, please. Can I think for 2 seconds? Jesus.
Wait, so the answer to this makes
It's badly written. So if he doesn't play the male lead, when they say will, okay, fine. When they say will, do they mean, they're not clear if they mean she's willing to or she automatically plays it. You see what I mean?
It's one side condition.
It's a very badly written question.
We were trying this one out.
It doesn't mean, it's not saying like, okay, I'm willing to, like, there are too many possibilities. It's too vague. Yeah, go ahead.
it says that only if. So if Joanne plays the male lead, she has to play the young female.
Where does it say that? It says, in how many ways can the teacher cast the play if Jean will play the, all right, will play the young female, she'll play it.
Only if.
Okay, right. So if he plays the male lead, she plays that.
If
Now-
he plays something else, she plays
Something else as
too.
well.
Both.
She, or she may not play anything.
Yeah, so there are all the possibilities.
Yeah, okay, so, fine. So let's just do it by cases before I forget. Well, I mean, we're gonna do it by cases. So case 1. Jean, what is it? He plays, what the hell does he play?
Just say male lead and she plays
The
female.
female
Young plays.
will play the young female part.
And he
Yeah.
plays, what does he play?
The male lead.
Okay, so male role lead. That's locked. And then if he does that, she plays.
She plays the young.
No, is her name Jean or is it his name?
She is
Her
Jean.
name.
So what's his name?
Jovan.
With a G?
Yeah, J.
Oh. J-O?
Let's make it terrible.
Who wrote this thing? Okay, J-O plays male.
J-Lo.
J-Lo.
And J-E plays female role. What was it called? Young female.
Young.
Just make it like Romeo.
So sexist, this thing, eh?
Yeah.
That the male lead, it doesn't have to be, could be 150 years old, but
Just be.
like there's no mention of a young male
Yeah.
role or an old male role, it's just male roles. And then the women, of course, can never be older than 21, because that's also signed by.
Sure.
But when was the book written? 4 minutes left? Oh yeah, what? 3 minutes? I don't know how far we're gonna get. Okay, so let's do that. Let's see if we can get this first case done and then we can move on. Okay, so those two are locked, right? So if those two are locked, how many students are left? So I'm just gonna write it down here. So 9 male, what do we have? 9 female, right? Well, these drop down, this drops down to 8 male. That drops down to 8 female, right?
Both positions.
And there were a total of, how many total roles were there? Well, there were 5 male roles. So 5 male roles goes down to 4 male roles and 7 male roles.
Female.
Female roles go down to 6 female roles. So, these are the okay. These are the number of positions we have to fill, right? Positions to fill. Positions to fill. Now wait a minute. I don't think it's choose. I think it's P, because I'm assuming every position is
order.
like you're playing the.
Yeah, order counts.
You're playing the whatever male, or you're playing the old female. I'm making fun of this thing. Okay, so this is going to be. Okay, so this is just going to be 8P4, right? Agreed so far?
Yeah.
And then
8P6.
8P6. Now here's the thing. Am I injecting any order here? Should I divide by 2 factorial? I'm multiplying 2 objects.
No.
Why? Because this is on
Oh,
X.
it's different variables, that's why.
Yeah. Why is this? Why are they different variables? This is the choice of.
Male.
For 2 reasons. Number one, you're choosing 4 people, here you're choosing 6, but here you're choosing from males to fill male roles. So they're different, they're independent positions. You would never see the doubling up of the order on the tree. So that's all good. So that's case 1. And what does that work out to? I don't know.
Times 8P6 equals, whoa, it's a big number.
What is it?
33,868,800.
Oh. Okay. So we leave that alone for now. And then next class we'll finish this off.